it's going to be some comparison added with some other comparison, or it's going to be some comparison or with some comparison. So here we've seen if A is greater than or equal to 0 and A is less than or equal to 9. We've seen this before. Then do something. Or if P is equal to 1 or P is equal to 2, do something. So these are the complex conditions. We got an and or an or. So let's take a look at what we would take to do an and. You can see it right here. And note what I'm doing here. I'm printing up or not up. And let's take a look at this. Actually has some kind of meaning. What am I doing right here? What's this condition? Does anybody tell me what this condition is doing? And this is kind of telling what it's doing. What am I doing here? Anybody want to shout it out? Type it into the chat. It's mostly uppercase. I'm asking the question, am I an uppercase letter? That's what that check is right there. Thank you. Yeah. And if I'm not an uppercase letter, I'm a lowercase letter. I'm not saying lowercase. I'm saying I'm not an uppercase letter. So I'm an uppercase letter or I'm not an uppercase letter. And that's what the condition's all about. All right. So the other way I could implement this is, and take a look now, this is going to be fast. So notice this up right here, and this not up right here. So here I'm saying this is uppercase. If it's an A, B, C, D, all the way up to Z, it's an uppercase. Otherwise, it's not an uppercase. Carefully watch this now, and mostly watch right here in this condition. Watch it. Watch it. Did everybody see that? I switched these two. I De Morganed this. Did you see it? This was greater than or equal. This was less than or equal. What's the not of greater than or equal? Less than. What's the not of less than or equal than? Equal? Greater than. And then remember what we did with De Morgan. We do the or. So I'm able to or these two things. Or excuse me, swap these two things. By just applying De Morgan to this expression, I can swap the else condition with the then condition. Clause, I should say. Any questions about that? It's kind of an important point. If I apply De Morgan to the condition, I can swap the else clause with the then clause. Here, I'll just put them side by side and you'll really see it. It's utterly clear. Okay, here's the and I've got up. Here I've got not up. Notice the difference between these two conditions. This is not this by applying De Morgan. Not greater than or equal, not and changes to or, not greater than changes to less than or equal. And here I've got it. So here I've got my two conditions. All right, so let's take a look at what it would take to implement the and in assembly language. It's not easy, but it's not crazy hard either. So let's take a look at it. So here's the and. So I'm implementing this condition up there. Everything else is just fine. Let's take a look though, just to make sure everybody's comfortable with it. So here I've got my up string, up, and that S on the end, this is up, and I'm just calling it, this is my up string. Well, what is it in ASCII? Well, it's up, but then I have to have my \n, and then of course I have to add the \x00 to tell stir-o right here that, oh yeah, that's the end of the string. Stir-o needs that. And I don't get it for free like I do in C. What's not up string, nups, is not up \n terminated with a \0. Branch around these data declarations. Oh, here's my C, by the way, but everybody knows this by now. Dot uninitialized C, dot block 1. Branch around this domain. Here's my nop 0, no big deal. I'm reading in from input Fox Charlie 15 or care capital I-N, comma D. Got my input. Now let's look at this condition. This is where all this in blue is to implement this and condition right here. So first what I'm going to do is say if compare byte accumulator, and I'm looking at see if it's A. Look at that. Compare byte accumulator A. Branch, ooh, look at that. I've got the condition. I'm saying greater than or equal. Ooh, look at that. Greater than or equal. I'm branching to nup. So let's look at nup, and that's stero, not ups. So if it's greater than or false, not upper. So that's what it is. So first what I do is branch greater than or equal to C2. Branch greater than or equal C2. So I've read in oh, here, I'm looking for C2. I'm thinking it's up here. Branch C2 right here. So I'm branch greater than or equal to C2. So it's greater than or equal. I'm going to C2. I'm not following through. I'm going to C2. And then I branch to nup. If I fall into this thing false, it's not upper. So if it's true, it might be uppercase. But with an and, it's got to be true anded with true. So the jury's still out. So I compare to A. Yeah, it's greater than A. Branch greater than or equal. It's greater than or equal to A. But is it less than or equal to Z? Let's go and see. And so now here I compare to Z. Branch less than or equal to up. So yeah, it is. All good. Less than or equal. So I'm up. Otherwise, branch to not up. And then this branches to end up, and I skip around it. So I've gone to a heck of a lot of trouble to support that and. This and condition. So I'm doing this branch greater than or equal, branch not. This is all to support an and. And so what I want you to take away is ands are kind of hard to implement in assembly language. Ands are kind of hard to implement in assembly language. So what would we do? How do we turn an and into an or? You all know this. You apply, you nod it. De Morgan, you did it. Yes, exactly. Exactly. You apply De Morgan. And what's De Morgan say? I'm nodding it. So if I've got an and I nod it, I turn the and into an or. And I flip those conditions. And here it is. There it is. Let's take a look at this and see if it's any easier to implement. So here I've got the same data. Go ahead. I did. Let's take a look at that and. That's exactly what I did. I did a double branch. I had to branch here and I had to branch here. There's the double branch you're talking about. Exactly. If it's not this, branch out of it. If it's not this, branch out of it. Otherwise, fall into it. What a pain. Take a look at this. So I applied De Morgan to this thing. The greater than or equal turns to a less than. The less than or equal turns to a greater than. And I put that in the or in the middle. Let's see if that's any easier. Well, let's take a look. So I compare byte accumulator to A, just like I did in the previous one, but I branch less than to not up. I mean, I go to not up right here, and I indicate that it's not up. It's not uppercase. Here, then I fall into this, and I go, well, if it's greater than Z, then it's not up, and I branch to not up. Otherwise, I fall into, yeah, it's uppercase. Now, if you're not sold on the fact that this is easier than the and, let's put them side by side. Whoops. Oh, look at that. Here's the and. Here's the or. I think the or is a little bit easier. So in general, and here comes the big statement, okay? In general, when working with complex conditions, those that have an and or an or, invert and expressions into or expressions by using the De Morgan to simplify the implementation. It's critical. You all understand that. You've got an and. You should flip it to an or by applying De Morgan to it. Change the and to an or and invert the greater than or equal to a less than and that sort of thing. All right? So that's an assembly language programming technique is that we don't generally like implementing in assembly language and expressions. We much prefer the or expressions. All right. So let's take a look at that technique. So there are some cases where you'll have C code like this, where you have the and De Morganing it isn't really much of a condition where you want to print out up. So in C, the way that we would implement this is like this. I've actually implemented this in my programming career, and that is that it's usually a little bit more complex than this condition. Otherwise, I'd normally just De Morgan this and move the printf into that then clause. But sometimes these are pretty complex instructions where, you know what, knotting this thing would just look ugly. And so this is just so much easier, right? It's less than A or it's greater than Z. And so don't do anything. And then the else portion, we do this. So that's basically, I De Morgan the thing and then I did nothing. And it's a little bit easier to implement this in assembly language, again, because it's an or instead of an and. So even if I don't have a then clause, don't worry about it. Just go ahead and implement the or clause. So what we would do is this. So here we have the less than A, greater than Z, do nothing, otherwise print that it's in uppercase. So this is the condition, the or condition for not uppercase. And we only want to print out if it is uppercase. So how would we go about doing that? Well, first of all, we only need the output string uppercase. And I've got up to save space, make these things nice and brief. So we branched around this. Here's our character C. We kind of left it off here, the declaration of it, to keep things brief again. Come down to the main. We load that. We read in the character. And now here's my comparison. I'm comparing in the accumulator because I just read it in. Load byte accumulator, comparing in the accumulator to A. I branched less than to the end if. And branch greater than to the end if. Otherwise, then I fall into it's uppercase. Okay? So you just have to think about these things when you're doing it. And that is, I'm branched less than, if it's less than A, I just want to branch around it, otherwise fall into it. So that's the translation of this thing when you do have a condition where you're, you have an and, it doesn't make much sense to De Morgan it because you have a then clause where you're doing nothing, not a problem. Just go ahead and branch around it, do nothing. All right, any questions? All right, now this last portion, and I'll do this really quickly, is this. When you have these conditions, it kind of makes sense. So we're doing a break. So we don't need to De Morgan this because we're branching. So everybody should understand that now, that if we're going to do something like increment C, then we have to De Morgan this thing. But if we're doing something like breaking, where we would branch out of something, then we don't need to De Morgan this. Okay? Now, note that, so I have that's really nice that I have the less than here. So I could say branch less than, go to end if, and I have branch greater than, and I have GT right there. So it's all good, right? Less than, greater than. Now, just to let you know, some C programmers will actually do this. Yikes. Yeah. Not thrilled with it, never liked it, but you will see this in assembly language, or excuse me, in your C code. Mostly it's to avoid mistakes like equal, and using equal instead of equal, and you can't assign to a literal, so the C compiler will go, hey, what's going on here? You're using an assignment statement where the literal is the thing that you're assigning to. That's not allowed. And so people will do this. I have always been the person that comes on in and says, yeah, that actually works. My recommendation is don't use equal in if statements, and instead make your if statements actually readable, because nobody says if the character A is greater than the variable C. Nobody thinks like that. No one. And so this is a complete capitulation to that equals versus equals, and avoiding that. I've seen it used in a couple of places. And most of the time when I come on in, I tell everybody, don't worry about it, switch it and make the code readable, and check for the assignment statements and if statements with some sort of syntax checker. But don't do this, because it impairs the readability of the code, because nobody thinks of literals compared to variables. Almost everybody thinks of variables compared to literals. You see what I mean by that? So this is a legacy carryover of the ability to do assignment statements and if-then else's, which you should never do. So the problem with this is that if you wanted to implement this as is, you'd have to switch your greater than to a less than. You'd have to switch your less than to a greater than. So to avoid that confusion, my recommendation is just to flip these things and have C less than A and C greater than Z. Okay? That's what my recommendation is when you implement these. All right. So let's really quickly look at the exercises associated with this and the kind of things that I would expect on an exam. And let's drop in and do the assignment really quickly. So this is the kind of thing that I would have on an exam. The exams look like this. The exercises look like this. And that is, I give you a C program and I say, okay, here's what it looks like in assembly language. But I want you to fill in A, B, C, and D. All right? And sometimes I throw in little gimmies like A. So what am I doing here? What is A? Does anybody want to shout it out? I'm branching around the data declarations. This is very common. Almost all the examples that I gave you, I branched to what? Anybody want to shout it out? Oh no. I'm main, you bet. In all the examples I showed you, I branched around these data declarations by branching to main. So what you want to do is pick main. And I usually put that in there for a gimme. That's just to give you a point. If you're struggling with what am I branching to on the first instruction, I mean, I'm always branching to main. And so that's why I say this is a gimme, branch to main. Okay, now these others, not so easy, but if I'm reading from Fox Charlie 15, it's got to be a load. This has got to be an LD instruction at least. And furthermore, I can only read bytes from Fox Charlie 15 or care in. So therefore, it's got to be an LDB. So the only question is am I reading into the accumulator or the index register? Well, down here, I'm outputting the accumulator to Fox Charlie 16. That gives me the output. So this has got to be an LDBA. And that's about the hardest part to these assignments is he using the index register or is he using the accumulator? And so you have to use context clues. Well, is he using the accumulator anywhere else? Oh, yeah, he is right down here. You got to be a little bit contextual here. You've got to start looking around. Right, cyber detective. So I'm not handing it to you on a silver platter. I'm kind of making you work it, okay? And so, yeah, you know this is an LDB. It's got to be. Accumulator or index register is the only thing that's up in the air about this. And you have to look down here and go, yeah, it's the accumulator. Okay, so that's done. That's an LDBA. What about the next one? Well, Gee, I mean, what are we doing here? This is comparing C to X. So we're asking if C is equal to X, we're doing something. Oh, okay. So we're comparing to X. This has got to be the comparison right here. So this has got to be a CP command or instruction. So we know it's a comparison, CP. The question is it a byte or word? But we're working with a comparison. So it's a CPB. Then the question is it CPBA or is it CPB? I'm sorry. Yeah, I did this one. Right. So we're on C. So is it a CPBA or is it a CPBX? Well, we already established that it's the accumulator. So this is going to be a CPBA. It's got to be to get that comparison right there. Now, what are we going to end if on? Well, that's interesting. If it's equal to X, we want to print it out. If it's not equal to X, we want to jump around it. Given that branching is the only tool available to us, we want to branch not equal to X. So this has got to be a BRNE, not equal. And that's what we've got here. There are the answers. Branch to main, LDBA, CPBA, branch not equal. So this looks very much like the kind of questions that I have on the assignments and the exams, and they're not easy. A lot of students struggle with them, so you want to get good at them. You've got to do the assignments, you've got to do the practice exams, you've got to get good at these, you've got to do our projects. And speaking of our projects, let's jump on in. Somebody sent me a message that's pretty funny. Yeah, I'm going to have to mute Brandon so that I get some of you others involved, because I know all of you know the answers to some of these questions, but are just a little bit shy. And I want to encourage you to jump on in. And by the way, I know I've said this before, if you answer incorrectly, that's okay. There is such a disparity between those people who have taken the first computer science class versus those people who have taken this is their third or fourth class. So it's okay to be wrong, but I want to make sure that you're involved and thinking about the lecture and not just tuning out. And the best way that I can do that is by asking questions. But I don't want to call on people and put them on the spot. By all means, feel free and throw out a guess. It's okay. We'll work through your guess, okay? And there's nothing to be embarrassed about, all right? Okay, so let's work on that project now. So let me end this slideshow, and let's jump on into the project. And so the way that you're going to get to that project is you're going to go ahead and go to the syllabus. We have it right here. And project 2A is due today at midnight, but that's okay. We're going to finish it up now. All right. So here we are at 2A. If this was, if I was in the student view, you'd have to start this. So by all means, you can start it. And one of the things that it says is, well, you're going to kind of need 1A, project 1A. So let me bring up 1A. I'm going to bring that up right here and show it to you all. Prep that so that I have it easily available to me. Where's my project 1A? Oh, come on. I'm going to have to search for it. Darn. I'm sitting right there in my downloads. Project 1A. There we go. 1A. Boy, it's really big. Okay. I'm going to shrink this down a little bit so we can get it on one screen, but I'm going to remind you what project 1A looks like. And your variable names might be, well, this is 1B. Not happy about that because it says 1A. Let's see, I think I can change 1A. Save as 1A, really? 1A. Really? txt. So, and let me just get rid of the comparison here. And this is 1A essentially. Okay. And bring it over now. So you all should have something similar to this. And I'm going to change this to 1A. All right, you should have something very similar to this. We have two uninitialized variables declared. I'm not sure what the names are, cin versus n value. It might be c, whatever you have, that's fine. And then we have an infinite for loop. We're reading in a character, writing out a character, and we're going to put a condition here in the middle. For right now, what we want to do is just implement something that is just going to read in a character and output its value in decimal. All right? So let's implement this in C, and I'll bring this on over so that we can see it implemented. But what you want to do right now is bring up PEP9. You should have an icon like this, PEP9. So bring it up, PEP9. Bring it up, there it is. Everybody see that? And let's go ahead and take a look at what we would do to translate this program into C. And again, for right now, the only things I'm going to focus in on are the data declaration, reading in input, and outputting, because I like to take little baby steps when I'm making implementations. So the first thing we're going to do to implement this is let's do the data declarations. And let me see if I can get this over to the left. It's going to be kind of cramped, but let's see if I can. It's over to the right. Bring this back up again, and let's see if I can't. Oh, I wish that would have gone over. I've got a little space here to get that. There we go. Right there like that. That gives me a little space here. Okay? So I'm going to just hold these things side by side so that you can follow along with me. First thing you want to do. So everybody got their PEP9 up. Everybody's writing code, right? First thing you want to do is I hit tab because I'm not going to put a label on this, but I'm going to do a branch. There's a branch command, br. And I'm going to branch main. Brandon knows that. Okay, branch main. Got here, I'm going to put main, colon, and I'm going to put not 0. And I'm going to put stop and .end. This is our basic minimal program. Does nothing but, does nothing. Does nothing. We're going to fill in the blanks. So if you run it, everything's good. We didn't get any errors. We got ourselves a working program that does absolutely nothing. Now let's make it do something. Okay, so the first thing that we want to do is I just wanted to read in a character. Oh, but let's do the data declarations. I'm sorry, I got a little bit ahead of myself. Let's do the data declarations. Uninitialized variable. What are we going to use? It's uninitialized. What are we going to use? .block, .word, or .char. .block. If it's uninitialized, we're using .block. Use the name here, cin. You use whatever's in your program, okay? Use whatever's in your program for that character declaration that we made. All right, cin.block. And it's a character, so it's 1. If it was a word, it'd be 2. But it's a character, char cin. Okay, now we have an uninitialized integer, so we're going to be able to hold them side by side here. It's called value, so we'll type value, colon. It's uninitialized, so it's .block. Is it an integer? If it's an integer, it's 2. If it's a character, it's 1. So here you see them side by side. There we are. All right? So there's our data declarations. You should be able to do this. If it's initialized, uninitialized, character, and int. So there's 4 different combinations that you have to be able to handle on the exams. Initialized, uninitialized character and int. So it's four different ways that you would declare things. These are uninitialized, so we use dot block. All right, now let's just focus in on the scanf and the printf for right now and see if we can get it doing IO for us. All right. Okay, so how do we read in a character in IO? That's where we use the Fox Charlie 15 or KRN. So we're going to LD, we load a byte B. We're loading in a character, LDBA. All right, we read from, we could say 0x Fox Charlie 15, but fortunately, PEP9 has said we're going to equate the symbol char in to 0x Fox Charlie 15. So we can say char in. Now, is char in a memory address or is it a value? All I'm asking is it a value or a memory address? Can anybody tell me? Is char in Fox Charlie 15 a memory address or a value? It's a memory address, right? That Fox Charlie 15 is a special memory address that is connected to the IO system that allows me to read from input. Since it's a memory address, we have to use D. It's not a value, it's a memory address. We must use comma D, direct addressing mode. So that allows us to read a character from input. You know what? And we're at a point where we've actually got a working program. We could look at the accumulator and find out whether or not we read a character in. So let's see if we've got that working correctly. Well, how do we set up input? Well, we've got batch IO and we've got terminal IO. So what we want to do is just go ahead and set up batch IO. What's the batch IO? We have to go back to our assignment, and that was over here, I think right here. And there's our input. So everybody go here, hit, whoop, don't want to get it all, just want this little bit. And we want to do is do a Command C or Control C. Command C if you're on Mac, Control C if you're on Windows, lowercase that. And what we're going to do is hit Control V if you're on Windows, Command V if you're on a Mac. And there it is. So we've got our input. So this program right now really does nothing other than we're going to be able to look to see if the accumulator read in that ASCII character 0. Let's see. So if everybody's got this in there, let's go ahead and see if the accumulator gets 0 into it. Look at that. So if we remember correctly from our ASCII, you'd be able to look at the ASCII characters. You'd find that the ASCII character 0 is in fact 48. And in hexadecimal, it's 30. But if you can't remember that, not a problem. You can actually use this little tool up at the top where you can type in a decimal value, 48, and it will translate it into hex, binary, ASCII, and on the off chance that it might be a command, it will print out the command here. But in this particular case, we're only interested in that it is the ASCII character 0. Pretty cool, though. This is a nice little thing that will help you avoid going to the ASCII chart. All right? So anyway, we've got a running program, and that is it reads in this character right here from input. Okay. Well, we're feeling pretty good about that. But what if we wanted to produce output? What we want to do is take that 0 and put it on the output. Let's go ahead and do that. How would we do that? Well, I'm coming over here, and it's going to be very close to the load byte accumulator char in, except it's going to be, what's the opposite of load? Anybody? Opposite of load. I'm just trying to keep you engaged so you don't fall asleep on me. Opposite of load is, if we're not loading, we're storing. Load and store, load and store. So we have a load here. Now what we want to do is a store, ST. store byte accumulator. So we've got into the accumulator the character that we read in, which is the ASCII character 0, which is decimal 48, hexadecimal 30. Read that in. Storing it, well, we can't store it to care in. That will do nothing. I don't even know what will happen if we did that. It might be that the world ends. But we do know that we could put here 0x Fox Charlie 16. And that's output address. But there's an equate for us, which is really kind of nice, which is care out. And I've got these all in the quick reference guide for you. So you can just go to the quick reference guide if you want, wondering which these things are. Now, what this should do is produce 0 on the output. Let's run it. There it is. Okay, so we've got a program, and this is, again, me as a developer, I always like to just take little baby steps and get a working program, try it, and go, okay, that works. Now, what else do I want to do? Well, what I want to do is I want to read all of these in. I want to ultimately output 48. I want to output the value. But why don't we just go ahead and output right now all of these? And so what I want to do is I want to loop on this. And so this is going to be a loop. I can put a loop label on this right there. And I can branch to loop. And this doesn't handle end of file, but let's see what happens when I run this program. All we're doing is these two instructions. We're going to output 0, 1, 2, 3, but we're not handling the X portion yet. We're not handling that. But again, little baby steps. What will happen? We might, well, I mean, we probably took some error or something like, oh, there it is. Yeah, so it's not liking that. So let's stop the program. Here's stop. Stop that program. Oh, okay, error, failed to perform memory. Yeah, I imagine you had a little trouble. Thank you. So yeah, it didn't like the fact that I kept on reading from memory, even though there was no input on that memory. So you can see I hit that X. I didn't do anything like stop. I kept on reading, and clearly PEP9 didn't like that. I started reading whatever, and I couldn't output it. And then finally I got to a memory address that I couldn't output something. So this is its way of saying, that's not an ASCII character, so I'm just going to print out this little box thing to let you know I don't know what that character is, but you've got 8 bits of something. That's what that box is all about. So what we need to do is stop on X, right? We need to stop on X. So how are we going to do that? Well, we've got the character in there. We need to compare it. We need to say compare byte accumulator. So we're going to compare the byte accumulator to what? Look at it. Here's our comparison right here. What are we comparing to? It's sitting right here in front of you. We're looking for what? I highlighted it. So somebody just say it. So I know somebody's with me, and I'm not just talking to myself. If it has to be Brandon, it has to be Brandon.
X.
Thank you. We're comparing X. Now, is X a value or a memory address? Just look at it. Is it a value or a memory address? It's a value, right? That's not a memory address. That's not a memory address. The memory addresses are like Fox Charlie 15, Fox Charlie 16. Those are memory addresses. That's a value. That's clearly a value. I've got these little ticks around it. That's a value. So that means it's an I. I'm comparing to the value, and I use an I, not a D. Okay? These were memory addresses, so I use a D. Memory address, I use a D. This is a value, I use an I. So I'm now comparing to what's in the accumulator to the value X. I just did it right there. Now, if it's equal, look at this. I want to break, so I can use equal. So I can say branch equal quit, end. And so I'll put end loop. Okay? Well, I don't have end loop defined over here. So I kind of have to put an end loop. So end loop, colon, and then I can put another knob 0 right here. And there, I'm out of there. And who is it who answered that? Because it didn't sound like Brandon. Was it Bryce?
Yeah.
Thank you, Bryce. I appreciate you answering. And Brandon does too. All right, so there we are. Let's run this program, and all we're interested in here is whether or not we're getting A 0 through F. Let's run it. Fingers crossed, because we're almost out of time. Look at that. Look at the output. Okay, now remember, I wanted the value. I wanted the value that was in the output. So I wanted, instead of outputting the character 0, I wanted to output 48 and 49, 50, and so on. Okay, and so that's what this assignment calls for. So I have to get value into the CN into value. Well, not a problem. It's in the accumulator. Okay, and so what I need to do is I need to store it, right? It's in the accumulator. I need to store it into value so I can deco it. I'm outputting a decimal value. So I'm storing what's in the accumulator. And this time I'm just going ahead and say that I'm going to store word. All right. Even though I've got a byte in the accumulator, I want to store the whole word in there. So I'm going to store word from the accumulator, STWA, into value. What's value? Is it a value? And here's kind of a trick question. Is value a value, or is value a memory address? It's a memory address because it's a label, comma, D. So now I've got it sitting and stored in this memory address. So now, instead of store byte, I just commented that out, put a semicolon there. I want to deco value, comma, D. Because remember, deco takes a memory address, no registers. There it is. So now we should output 48, 49, and so on. 48, 49, 50, 51, 52, 53, and so on. All right? And then we jump when we hit the A. When we get to A, we do that jump. So it's 56, 57, and then we jump up to 65. There they are. Now, I don't know if I have a \n on this. Let's go ahead and go to the assignment, see if we're done. Real quick, let's go and look at the assignment. Right here. Oh, look at that. So I'm supposed to put these on separate lines. Okay, well, that's all right. We know how to do that because \n is just a character. And so I've got a store byte. I kind of want to move the store byte down here. And so I'll just move it down one line. I just selected the whole line, Command Control X, Command or Control V. And I'm going to store byte accumulator, but what I'm going to do is I need to load into the accumulator that \n. So LD, BA. Now, is \n a value, or is \n a memory address? Just look at it. Does that look like a memory address? It's a value, 100%. That is no way. This is a memory address. This is a value. This is a memory address. This is a memory address. This is a memory address. This is a value. This is a memory address. This is a memory address. Okay? So you can see when it's a value. If it's a value, it's a comma I. Okay? And now it's just a matter of storing what's in the accumulator care out, and we'll get that \n on each one of these lines. Let's take a look. Boom. There it is. And we are done with this assignment. All right? We're done. We're done. This is all that's to it. You've got to have this down in your code, but we're ready to store this thing now. What I want you to do is File, And this is, and so you can submit this as save source as, and you'll see it's untitled.pep. What you want to do is just say, we want to save this as text. So you're going to save this as, it's going to either be text. So you want to notice that .pep. You want to save this as project to a.txt. And I've already got one. So do you want to replace it? Yeah, sure, I want to replace it. So there I have it. Now what I want to do is pop over to my assignment. Okay, and I'm going to go into student view and we'll submit this thing. So I'm going over to the assignment. I'm going to go into student view so this looks just like the environment you have. You all hopefully started it already. Come on, I click student view. Come on. Come on. There we go. You started assignment already. So you're going down to the bottom. What you're going to do is choose file. You're going to go to that downloads directory. There's my project. Well, downloads. Wherever you saved it. I don't, all of a sudden I'm realizing I don't know where I saved that from PEP 9.